marche, hein?
Attends. C'est parti.
Peut-être qu'il faut les regarder si ça marche.
Je fais ça, mais il y a bien 10 secondes. Voilà, ça y est, on y est.
Who's A?
Okay, so let's.
Okay.
It's Dagmar, yeah, no? Yeah.
So, Olivier?
We
are on. Yes, I think
on YouTube
so.
Live.
Yes, we are live.
Yeah, so we hope it's all working. Welcome to everybody. We are really pleased to have you on the map. And I hope you had time to look at the introductive videos that explain how things will work during the next 2 days. In the next 2 days, videos of all the papers are already available in the area of the library area, and you can watch them whenever you like. And tomorrow, we will spend most of our time discussing and having a scientific discussion with the authors. So that's going to be plenty of time. You see, there are 2 sessions, one more likely to be interesting for Asian people, and the other one in the afternoon more for American people. At 12 o'clock, we have keynotes in order for anybody in Asia or Europe and America to be able to hear them. Just one comment to take to the authors of tomorrow. If we can meet all together in a room outside in a test area in the top left corner of the map, there's a small room called the test. If we can meet them at 8 o'clock, that would be very nice. Then we could discuss with the moderators, the authors of tomorrow, and the moderators of tomorrow to look at all the details of your call or speech for tomorrow. Nevertheless, tomorrow it will be nice to have all the speakers coming to the rooms at least 15 minutes before the speech. To try to recognize each other, speakers should have a blue hat. So, the chair, scientific chair, should also have a blue hat, and also the moderator should have a blue hat. The workshop leaders should have a green hat, and Romain will speak a bit about the workshop that took place the last 2 days. And the people who have a red hat are organizers. So me, I'm Olivier, the one who's moving on the stage at the moment, and I don't have the blue hat. I'm sorry, but I will have it tomorrow. So I leave now Cyril to explain about the book and other details, and after Romain will speak about the workshop. Welcome, Cyril.
Yes, thank you, Olivier. So I'm Cyril Dout, a member of the organizing committee, and I just wanted to add a little word about the way this room is working. What you are watching actually is a YouTube live of what is happening on the stage. So if you have questions, please use the comments of YouTube. We are parallelly watching YouTube, and if you want to ask something, please go on the stage when you need to ask. So as a member of the organizing committee, I was in charge of the collecting of the proceedings and editing of the book. And I would like to begin with giving you some news about the book. There was some issue in the last weeks about this COVID disease, and half of the team of the printer was actually out of work last week. So the book is currently being printed. It will be it should be printed and ready on Monday, and we will send it to you for the one who have ordered it as soon as possible. Speaking about the book, I would like to thank all our authors and all the members of the scientific committee who contributed to this amazing state-of-the-art on architectural geometry. The content of this book is presently already available in the library that you can find on the map, and with an electronic version and also the videos. This book was made possible and also this numerical environment thanks to our host institution, the École des Ponts and the Université Gustave Eiffel, and also thanks to our sponsors, two design offices, TES and Arcora, who will be also present during the conference. They both have pavilions that you can watch in the pavilion area that we will be showing you after these first two keynotes. And there are also two more sponsors, the Lafarge Chair on Sustainable Development, and also the scientific institution called LabEx MMCD, who support us, support the work of the Six Shell team from the very beginning. And yes, before leaving the floor to our first keynote, I let Romain having a few words about the workshop, he organized. So, thank you and welcome to AAG.
Okay, thank you, Cyril. So it's a pleasure to welcome you to AAG. So as you know, this year we had a particular situation to organize the conference, and it was also true for the workshop, which is a challenge in itself, because the workshops are moments to exchange ideas, experiments, and it's always difficult to do so remotely. So we would like to thank the workshop leaders who actually proposed to tackle this challenge and switch to a full online workshop, where initially they had submitted for in-presence workshop. And we would like also to thank the 62 workshop participants who really made this a success, I think. So just to sum up, we had a variety of topics that I think illustrate the activity of the AAG community, with a workshop on asymptotic grid shells. So a topic that will be presented in 2 publications during the conference. So it's also an active topic of research. And so thank you to Eike Schling, Jonas Schikore, Thomas Oberbichler for presenting this cutting-edge topic. So then we had also Vicky Sender and Matthew Tam, who did a very nice workshop on complex collapsible structures, which is a kind of spatial modular origami, which is also a topic that the AAG community enjoys, with several publications on this topic tomorrow. The third workshop was on robotic fabrication for segmented shells, and it was organized by Elena Shilova, Maria Aceitunu-Poch, and Taole Chen. And actually, for that, we had a part of the robotic fabrication that was done at École des Ponts, so we couldn't let go everything. And so part of AAG was with us in Paris in the end. So I would like also to thank the Malo, Charrier, and Julien Glatt, who are doing the robotic fabrication remotely, and also Al Robotics, who offer the support for this particular workshop. And 2 last workshops. So one with on structural form finding with machine learning, which was, I think, quite successful. Merging graphic statics, which is a topic dear to the heart of the AAG community, and machine learning, which is a new topic that we have to use and to to think how to use that to design better buildings. So the workshop leaders were Pierluigi D'Acunto, Vahid Moussavi, Vincenzo Reale, Patrick Ole Olbrock, Catherine Rankin, and Federico Bertagna. And the last but not least of the workshop was the workshop on topology finding with the Compass framework. So which was tutored by Robin Val, Johnny Lee, and Tom Van Mel. It was also, I think, quite successful from the feedback I had from some participants. So I hovered through the chat rooms today and yesterday, and I must say I was quite impressed with the results of the workshop. So if you want to learn more about those workshops, please note that we will upload their outputs on the map within the workshop rooms, and that the workshop organizer will be also present during the conference. So I think they will be happy to answer your question or exchange about what they have done. So please engage the discussion. So thanks again for the workshop organizers and the participants. And now I leave the floor to Olivier.
Yeah, thank you, Romain. I think we can now start our first keynote. So I will ask Tristan and Stacy to come on the stage. I think Tristan was just around. So there's a slight delay. So I think we have to wait 4 or 5 seconds for Tristan to catch the information. Hope Stacy is around as well. Hello, Tristan.
Hello, can you hear me?
Yeah, Stacy is arriving, I think. Yeah, we can hear you. Stacy has to come on the stage. Yeah, it should be okay. Very good.
Perfect, it works.
So, one word about keynotes. Keynotes are, some of them are pre-recorded, which is the case of this first keynote, and some others will be performed live. So this first keynote, Stacy and Tristan are here. They have pre-recorded their video, and they will be here for questions. For questions, you can ask questions on the YouTube channel directly, and also maybe we will have a try. If you dare, at the end of the broadcasting of the video, if someone wants to ask a question, he could come on the stage and ask live its question. So if you stay in the area for watching YouTube Live, you can only write comments. If you want to speak directly, you have to come on the stage. We will see how it works. But I think I should introduce this first keynote. So we have the chance to have Stacy Eisenberg and Tristan Israel. They're both working in the famous architect company called Atelier Jean Nouvel. And they're going to show us their work through 3 main projects. I think Cyril can maybe start to send the video YouTube directly. We go for 30-35 minutes of broadcasting, and after we go for questions.
Hello, I'm Tristan Israel. I'm project architect and computational designer.
I'm Stacy Eisenberg. I'm a project manager and I specialize in facade design.
So in this keynote, we are going to present you the Jean Nouvel design philosophy and how architects transform each unique concept to geometry and challenging building. So who we are? So Atelier Jean Nouvel is a French architectural company based in Paris and led by Jean Nouvel. We are 125 people working on building worldwide. And what we do? So basically, we're working on architectural buildings, but civic buildings, offices, housing, interior design, and even urban design. What we are going to present to you in this keynote is our expertise through three main projects: the Louvre Museum in Abu Dhabi, the Duo Office Towers in Paris, and Materazzo, a residential and hospitality high-rise tower in Sao Paulo.
So the first case study is the Louvre Abu Dhabi with its feature dome. The Louvre Abu Dhabi is located on the Sadayat Island in Abu Dhabi in the United Arab Emirates. Its gross surface area is 63,000 square meters. Its net surface area is 22,500. The dates of the design were from 2007 to 2015, and the construction from 2013 to 2017. The building is a classical art museum, and it's situated in the new cultural district on Sadayat Island. There's a 30-year cultural accord with the Louvre and Agence France Musée, Paris, for long-term loans and acquisition assistance. The museum is considered to be a museum city. It has permanent and temporary exhibition spaces, children's museums, auditoriums, restaurants, cafes, boutiques, an administration building, and art workshops and storage areas. The Sadayat Island was conceived as a cultural district. Several well-known architects were to build renowned projects on the island. The AAG2020 project is the Louvre Abu Dhabi. The Frank Gehry project, Guggenheim Museum, is also under construction, and there would have been, or will be, a performing arts center by Zaha Hadid, a maritime museum construction, and there would have been, or will be, a performing arts center by Zaha Hadid, a maritime museum by Tadao Ando, and a Zayed National Museum by Fosters and Partners. Generally, when we begin a project, there are many areas of research for the concept of the design. And most of these areas of research are based on the content and the specificity of the place. There are three grand areas. One is the place, the geography, the history, the culture. In this case, it's where the desert meets the sea and that border. We also look very closely at the history and the typologies, and in this case, the museum city and the layering of the archaeologies of the area. And then there's the vernacular, the climate, and the environment. And these are ways of looking at traditional approaches and dealing with the microclimate and the features such as shade, shelter, and sunlight. These are some of the initial sketches done by Jean Nouvel. These are some of the initial massing plans, and there are two key elements in these massing plans. In this one, there's the water element, which is the blurring of the boundaries between the desert and the sea. And the second key element was the dome, and that was the incorporation of very specific light and shade. The basic geometry of the dome. The dome is a slice of a 349-meter diameter sphere with a span of 180 meters and a rise of 25 meters. At the base, there's a support, a belt truss, which is 6 meters deep. There are also 4 structural support elements which span 110 meters between supports, which are hidden within the buildings of the museum. The dome. The primary structural grid is a structural steel space frame, 6 meters deep, made of 10,000 structural components, pre-assembled into 85 supersized elements, each weighing on average 50 tons. Structure and cladding. There are 8 layers of cladding. There are 4 outer layers clad in stainless steel and 4 inner layers clad in aluminum. There are 7,850 unique stars, creating a layered series of geometric patterns, allowing for approximately 1.8% of the dome to be perforated. The base pattern is an isosceles triangle, repeated, rotated, scaled up and down to form a system of squares and hexagons. Pattern then mapped onto the dome surface to be true at the apex and distorting outwards towards the perimeter. The cladding patterns used to control the light, intensity, the direct sunlight, and the temperature. Structure and layers. The base structural steel space frame also formed a pattern. as well as the framing assembly, and then the cladding assembly, the layers of the cladding assembly, to achieve light attenuation as well as light control. And these are some of the studies and the long research that was done on the different openings within the dome. And images from the exterior of the museum and the dome. The dome acts as a light filter as well as a light source. And the research that was done through various mapping techniques. There was a light intention map to analyze the light and temperature controls, an inverse lighting analysis, which analyzed the light and shadow, and a transparency map, which analyzed the perforations mapped out and translated. So these are views of the lights moving and the patterns moving and the different types of patterns throughout the day. And these were calculated with the angle of the light and the incidence of the type of light as well as the type of pattern. And this is a conceptual image of the rain of light, the light typology and the light patterns. We did many study models, some in-house, to analyze the light, shadow, as well as the different perforations. These were done outside of the office. There was a prototype model done at 1:33 scale. And then there was a full-scale mock-up and prototype. The preliminary study showed 10 distinct superimposed layers of cut aluminum panels. And the light variation was analyzed for its intricacy, and the structure maintained consistent points of connection. There was also analysis of the temperature to be included in the studies for the microclimate underneath the dome. The preliminary prototype was built on site. You can see the beginnings of the cranes behind. This is a view from the exterior. And this is a view from the interior where the analysis was done on the different lines of the rain of light, as well as the light that was captured within the dome itself, and mostly the patterns on the floor and the walls as they moved throughout the day and changed their sharpness and their forms. We constantly refer back to the conceptual images while we're doing these studies to keep in tune with the original ideas that were put out in the 3D renders. So these are the first images of the construction site with the prototype to the left. The first images of the dome with the museum underneath, under construction. The patterning of the stars as they go into place on the dome. The positioning of the stars and the different layers. A view from a distance. And the last piece of the dome cladding was installed in 2015. And these are views of the final project from the interior inner courts out towards the sea. The inner courts looking up towards the dome, as well as the gangways inside the dome. And then the light patterns. So once again, the light was not just a rain of light. The light was also captured within the dome and lit up areas of the dome. But mostly the analysis was also on this kinetic form of light as it was transferred through the dome onto the areas below. How it moved, how it vibrated with the water patterns and the angling of the sun. At the end of the day, the patterns became very long and very soft. In the morning, they were sharp and much more concise. These are on the water areas. And as the sun goes down, the night views have also a kinetic to them, as if this was a celestial vault. The stars come out from underneath the dome.
We're moving now to Paris. And we're going to present the project called Tour Duo. So the client is Ivanhoe Cambridge and Heinz, and the program is like offices and hotel and retail, and a restaurant on the upper part of the first tower. We won this competition in 2012, and the construction started in 2017. We are going to deliver this project for the end of the year. So located in the eastern part of Paris, near the Seine, Duo is composed by 2 towers and a large public plaza. They are the last building at the end of the Avenue de France, and they are facing the Ring Road and an impressive opening on the railway. So the very idea from Jean Nouvel was to reveal this urban landscape, invisible from the ground. All the movement from the train and cars crossing the bridge has to become part of the tower's identity. So the project geometry starts from this intention to play with the reflection. At the really beginning, we wanted to create dynamic patterns composed by the reflection of the surrounding. Sometimes it could be really clear and sometimes more abstract, and to have an interaction between the inside and the outside of the building. In order to reveal the tower from the main avenue and capture the reflection of the ground activity, Jean Nouvel decided to dramatically incline the towers. As you can see on this picture, the tower slightly coming in the street. And all this inclination permits to emphasize the reflection of the train and the cars. Here is like some renders at the very beginning of the project. So from the Avenue de France. And here from the Ring Road during the day and during the night. What is really important too, once the massing is decided, is the vocabulary. The vocabulary is each piece of this building had to refer to the world of train, vegetation, and moving lights. So we choose to illustrate through 2 key elements of the project: the reflection of the double skin facade of Duo 1, that is the tower on the right side, and the curved bristle of Duo 2 on the left side. So the first step was to precisely map the context to validate and control the initial idea. So here on Duo 1, we decided to use a double skin facade, and to realize this intention, we composed the facade thanks to 8 families. The first skin of laminated glass is porous and designed to both control thermal condition and reflect the context. The second skin ensures the air tightness and the fire protection thanks to the catwalk and the shadow box. All those geometry are drawn in a beam model in which all facade family are precisely referred and informed. In this beam model, we have all the information about the curtain wall and all the information about each piece of glass. So if there is an element like the height of the floor that is going to change, we are able to adapt all the project. One important point was to control the impact of the sun reflection on the ring road, and so we adapt the scale and the angle to comply to the city ring road requirement. As you can see on those slides, we are sure that we are not going to have any problem, any issue with the car because of the reflection of the sun on the road. We always control the geometry thanks to renders and thanks to visual mock-up, like small prototypes like this, 3D printed. And when it's decided, we jump to the full-scale mock-up, as you can see here, and we were really happy to see that the effect that we were looking for was present. As you can see on this image, you can have like the people inside and people outside. It's like blurring the reflection of the context, and it permits to have a play with the surrounding as we wanted at the beginning. the construction. So basically, this is an image where you can see like the reflection of the road on the facade. So works pretty good. And from the ring road, you can have, as you can see here, all the railway reflected into the facade with a gradient from the sky reflection to the ground. And as the light is changing during the day, we discovered like a really interesting effect of the reflection of the glass tube. Here we are going to present you like a small video because this effect was really important for Jean Nouvel as a dynamic effect. And all the cars are visible from a pedestrian point of view, and so all the context is revealed thanks to the tower. The second element is the brise-soleil of Duo 2, and in order to realize the intention of this wavy reflection, we imagine a highly reflective curtain wall with a curved brise-soleil. The geometry is a balance between needed solar protection, clean, clear view visibility wanted from the client, and important structural constraint, especially from the wind. Each blade is a 3-meter aluminum triangular profile combined with a 2 millimeter thin sheet of reflective steel. We control all the time the effect from the inside too, with this render, for instance. And all the geometry is coming from a complex computational design which takes in consideration the initial graphic wavy ID and the construction constraint. Here, from the generative surfaces to triangular profile and to curvature optimization. Indeed, to reduce the cost, we sort all the blade according to the curvature and achieve a simplification of 50% of the blades that we transform to straight profile. Here is like a video, a render video to control the large-scale effect. And it's like if you're moving away from the tower and all the surrounding is playing with the sky and everything is moving into this facade. When you're getting a little bit closer, you can start to see the context and how the railway is creating a really abstract motif thanks to this triangular element and the reflection of the brise-soleil. So all these elements are confirmed thanks to models and visual mockup again. So this is the really first visual mockup we made. So it's 3 pieces of aluminum. We tried in steel, in aluminum, different metal. And here is this 1-scale blade in reflective steel. Full-scale mockup, and some images of the construction. From the Avenue de France, we slightly distinguish the facade and the brises. And when you arrive near the tower, the effect becomes more powerful, and the surrounding is playing into this facade. It's really interesting to see it by night too, because when you're on the plaza, near the tower, you can see the light of the train going through all the facade. This is basically 1 week ago, and as we said, this project will be delivered by the end of the year.
The next project and final project is the Matarazzo Tower in Sao Paulo, Brazil. One of the original rendered images, conceptual images. So the location is the capital, Sao Paulo of Brazil. The project gross to net surface area is 54,000 square meters to 36,700 square meters. The height of the tower is 93 meters. There are 22 stories. The client is Alexandre Allard, and the design dates were from 2012 to 2016, and construction from 2017 to 2022 will be the completion date. This project is a renovation and a redevelopment of the historic buildings of the Matarazzo Hospital and site into a multi-use hospitality, office, residential, and hotel complex. It's also a revitalization of the urban center of the Paulista area in Sao Paulo. The high-rise tower, combined with the Matarazzo maternity ward, will become a 5-star Palace Rosewood Hotel. 151 guest rooms, 122 owner suites, with amenities including restaurants, bars, lounges, terraces, gardens, swimming pools, a spa, and a fitness club, as well as a private penthouse at the top of the tower. The material one of the prime conceptual elements that was used on this project. Once again, we go from the concept to the context, the place, the geography, history, and culture, the density of the city, the vernacular and typologies, the layers and scales and patterns of the traditional favelas, well as the brise soleil. Being a temperate climate, the brise soleil are often used in Brazil. The climate and environment, which allowed us to interfere the exterior with the interior and bring the gardens inside. This is a sky view of the actual site, which is in the red square, and you can see the old hospital, as well as the surrounding density. The main idea for this context was that within this incredibly dense area, that Matarazzo traditionally represented a clearing, and this would be a clearing in the forest of urban density. So these are some of the preliminary concept sketches by Jean Nouvel, and some of the preliminary 3D concept sketches and layouts where we see the integration of the green into the layering of the external cladding areas. These are more 3D sketches of the preliminary layouts where we start to define how the cladding areas are layered and how they are opening one to the other. And some of the final concept images where we see the different brise soleil and the different greenery which is incorporated into the building. Because this was such a dense area, one of the ideas for the brise soleil was, of course, not just to protect the views in, but to allow for an animation of the views out. So we did many study models. These are some of the preliminary study models. Also preliminary study models where we started to define the layering of the brise soleil and the exterior cladding. A more evolved study model, which was built in Brazil, and some of the final showroom models. So the preliminary cladding and brise soleil studies. We did a prototype. The prototype was a showroom, so we were allowed the opportunity to define a duplex apartment, a simplex apartment, and a hotel room. The location is shown here on the Itapeva facade to the south. These are some of the 3D images of the showroom, which show the different studies on the brise soleil, as well as the cladding and glass splits. The geometry and density of the brise are driven by the heat calculations as well as the structural constraints. This is a sun protection study. On the left, you can see the glazing without the brise, on the right with the brise, which allowed us to calculate what the brise needed to be in terms of sun protection, intimacy, as well as views. These were one of the preliminary mock-ups of the brise soleil, which was done at the showroom on the area on the side of the garden. And this is the terrace area looking into the duplex apartment, which was built for the showroom mock-up. These are views from the inside out into the garden. The garden was also planted specifically for the prototype. To the left from the ground floor level and to the right from the mezzanine level. Some views of the interior and exterior Breeze. Some of the smaller terraces at the showroom, which were areas which included layering of the facade as well as the Brise Soleil, including in the layering was the reflection in the glass. And these were some of the Brise Soleil that were done to the exterior of the building with vegetation almost incorporated into the Breeze. There was also a prototype that was done for the facades as well as for the Brise Soleil and the terrace areas. This tested a lot of the different treatments to the Brise Soleil, which was a simile Corten steel, although these are aluminum extrusions, and the color is done with a fusion of a film onto the Breeze. This was one of our first projects with exposed concrete, so it was interesting to see the concrete and how it reacted. We tinted the concrete darker, and that was a large amount of research that was done so that it didn't separate out into, which you can see in the prototype. That was fixed for the actual construction. The Brise Soleil were, once again, we worked in families. So there were different typologies that were used throughout the building. Here we can see a sample of how they were calculated into the families. There were approximately 21 different families, and the typology analysis took into consideration the program of the interiors, the intimacy levels, the sun protections, the views in and out, the lighting patterns, as well as determining the orientation, the element patterns, the dimensions, and the spans. Of course, there were subfamilies to the 21 families. And this is the construction. Here we see the Matarazzo complex with the tower at approximately level 6 in the middle right-hand corner. This is the Matarazzo complex where we're almost at the topping out. We're at approximately the 21st level. This is an image in 2020 where most of the Breeze have been put in place and they're installing the glazing. These are some of the views of the different Brise Soleil from the southern side. The southern and the north side had most of the Breeze because that's where the buildings and the proximity to the other high-rise buildings were. So as a protective measure, all of the Breeze were put onto the north and the south, and the two other west and east facades were open, one to the city and the other to the garden with the terraces. Here we see once again the south side. This is the side facing the garden where the terraces will be implanted up and down this facade. Most of the facade will be green. This facade is relatively open. It looks out onto the Matarazzo complex. This is the Itapeva Plaza, which is the entry to the south side of the building. And this is the garden side of the facade, which is to the north. It also includes many Breeze. And we see to the right-hand side the west-facing facade, which is open to the downtown views. We have a short fly-through film of the latest construction.
So we hope you appreciate this presentation, and we hope to see you soon in Paris, Sao Paulo, or even Abu Dhabi. Thank you very much.
Thank you very much.
So thank you very much for this very nice presentation. Thank you very much for this. Cyril, did we get any question from YouTube Live? Your mic is off.
Yes. No, there are no questions during the live, but actually, so a few comments that I can confirm, because actually I live in Paris, and I can confirm that the shading device and the effect with light is actually working fine for the people walking just. So yes, it's really Reis. So it's a success from and I think that the intention has become a reality, and yes, I think it's really is working. I don't know if I think Romain had a question. He's back, I think. No, Olivier, your mic.
So, well, I have some comments or questions, but I also have two kids who are not really willing to let me ask the question at the moment.
So maybe I can ask a first question, and after people who are in the audience, if they have a question, they can move on stage. But maybe to initiate the discussion, I can ask a first question about these reflectors. You've shown very quickly the way you designed them, and so they are developable strips, and they are bent in a circular fashion, in a conical fashion. Tristan, can you give us?
Yes. Sure. So I guess you're talking about like the Duo project and the Curve Brise Soleil. So exactly. So it was a really interesting subject because at the very beginning we sought to bend like a triangular profile thanks to industrial machine, but in fact it was not the good solution. And so with the constructor, we preferred to unroll each face. So each face of the triangle is unrolled, and after they weld each face, and so the geometry is like a reconstruction of those three unrolled plates. And at the end, we have the last plate that is like the stainless steel plate that is an unrolled geometry too. And thanks to simple screw, we get the geometry that we needed.
Okay. But the stainless steel cover that you put, it comes in one strip?
Yes, correct. So you have, at the end, you have 4 stripes. You have 3 stripes to create the triangular profile, and 1 stripe that is the stainless steel screw on the triangular profile. And what was interesting is to simplify the model, because at the beginning, each element, something around 1,200 elements, all the elements are unique, and you can imagine that it's not really easy to build it. So we found a solution when the curvature of the element is more than 85 meters. We decide to create like a straight element, because your eyes is not able to see the difference between when the curvature is too high, it's the same. So we managed to reduce the cost and the construction of those elements thanks to this trick.
So how many different elements you had at the end?
1,161 elements. So it's a lot, but this is just for the bend triangular profile. But you have all the what we call braco. All the elements to fix on the facade, they are all different too. And so there is nearly 500 elements. All the elements are unique, and it was like an interesting exercise for the builder to place each one. And so we had to come on the construction site too to check if there is if everything is at a good place. And we had a few mistakes. So it's not easy to fix those mistakes when you're like 100 meter high. So sometimes it was a bit tricky, but we are really proud about like what Vinci and Batek have done on this project, because they successfully place all the elements.
Yeah, and you didn't. Well, you were pretty fast on the question. And what tool did you use to simulate the light and all the reflection? Because rendering was beautiful, but how did you make it?
Yeah, sure. So the idea of the presentation was more to present where the form is coming from. But I agree with you about like the technology. So basically, we are using like a Rhino, Grasshopper, and some Python scripting into the Grasshopper. And for the reflection, it's like especially for the issue about like the car, it's our own tool. And thanks to Ladybug, we were able to precisely calculate where the sun is going, especially on the road. And so it's all it's a conception between like a really advanced tool to understand and to verify like the first intuition.
Okay. So maybe now we will. It's our first try, but if anyone in the audience wants to ask a question, he should move on the stage.
Yeah.
If anyone dares to do it, I don't know. But there is no risk, I can tell you. There's a little slight delay, so that's why no one is moving at the moment.
Yeah. In the meanwhile, Romain has sent us. He can't talk because of personal reason, but he has sent us a quote from Le Corbusier about city planning, saying that the materials of city plannings are sky, space, trees, steel, and cement, in that order and that hierarchy. I think it fits quite well to the project. Or what do you say? The architecture from Le Corbusier is very different, but from the quote, it's not so far.
Yes, it's true. I think like in those three projects, what is really interesting is the way that we are using. We are strongly using the context and how the building are dealing with this context, and at the end the fusion of the building with the cultural context, not just the building itself, but so I think when you're talking about the sky, the green, all the things. It's really important to take in consideration not just like standards and all the constraint about like a structural constraint or whatever, but we need those buildings to be accepted by the people, and I think it's always strong ideas like those ones that are efficient and interesting for people who are going to use it. So maybe Stacy, if you want to say something about that too, you're welcome. Your mic, just your mic, Stacy.
I turned it off. Can you hear me?
Yes, that's fine.
Yeah, I think that it's a very sort of a controversial stance in that Jean Nouvel and our atelier, we consider ourselves to be contextual architects. And sometimes that doesn't sit well because contextual architecture usually uses a vernacular, which is sort of a standard, and we tend to play off of elements that exist that are not natural resources for the contextuality, but more perhaps emotional, and that gets us into trouble sometimes. But I think that the results can be quite spectacular because of the play on something that is not so conventional. So.
Okay, thank you. Maybe we can have a second try. Do anyone wants to dare to come on the stage to ask a question, a last question?
No one
Yes.
dares.
No, there's someone. There's someone. So put your mic on. I know, I think he moved away. Okay.
You must have your videos and mic on before you jump on the stage. It works better.
I think, yeah. So, well, unfortunately, we cannot hear the question that was proposed. But nevertheless, you can always speak after, during the socializing tour that will happen after the second keynote.
Olivia, there is a question from internet, and Felix is also trying a second attempt to jump on the stage. So maybe we wait.
Okay,
Felix.
but tell Felix to get out, put his mic on and his video on, and come back.
I think he has
from the stage. There's a slight delay.
Yeah, there is one question from the audience, if I have time. Yeah, about the Sao Paulo project. AAG2020 Nouvelle developed the entire performance-oriented design process, or was it made by IT cooperation with IT cooperation with a sustainability consultant? And
we had sustainability consultants, and we had, of course, we worked with Arup engineering the facades. So it's pretty rare that there's not an engineering core that helps us with all of our projects. But I think there's also an enormous collaboration, and we're lucky to be surrounded by a group of experts who can take into consideration some of our demands, which can seem to be a bit far-fetched, but we work with engineers who are very open-minded and are interested in research and development. So I think yeah, we're not engineers, we're architects, but we collaborate very closely with our engineering teams. So I don't know if that answers the question exactly.
Yeah.
Hope so.
So did Felix manage to come back?
Yeah, I don't know. It's Felix Amsberg. I try to trace him, but
Okay, so maybe he will have time to speak during the socializing time. Thank you again very much for your presentation and the very nice pre-recorded video that you did. Maybe we can move on to the next speaker. And so it's Pedro Reis. If Pedro is within the audience, please come to the stage. Yeah, I think he's around. Pedro is arriving. Good.
Perfect.
So, hello, Pedro.
Hello, can you hear me?
Yeah.
To get my video feed?
Yeah. Everything is working well. Thank you again, Stacy and Tristan. See you in the socializing video feed.
Thank you very much. Thank you.
Yeah.
Thank you again, Stacy and
Felix, Felix just managed to reach the stage, so maybe we can.
Thank you very much.
If it works, I will try.
Yes. Felix, just managed to reach the stage, so maybe we can.
Thank you very much.
Oh,
be careful, Felix. There's a delay in between the YouTube and what we're speaking, so
yes.
You should. Okay. So we're moving really to the second speaker, who is Pedro Reis, who's the director of the Flex Lab in EPFL, and he's also the president of the Society of Engineering. And this is an impressive position. Pedro is going to do his presentation live, so it's not a pre-recorded video. And I hope, Cyril, the streaming goes well and everything goes to YouTube Live in the same channel. So no one has to move. And now we leave the stage to Pedro.
Yeah. Very good. So this is not pre-recorded. Felix was just trying to get on stage, so that's the proof that this is not pre-recorded. Can someone just give a sign of life that you're seeing my PowerPoint slides?
Yes, it's working.
We can see it on YouTube. It's perfect.
Excellent. Very good. Okay, so thanks for the opportunity. This is not a community that I'm typically in contact with. I don't have a background in architecture. I do have a background in physics and mechanics, and over the past few years developed a strong interest in the power of geometry in a lot of the problems that we look at. So today I want to tell you about the usage of mechanical instability, specifically buckling, for generating complex structures, and we'll focus specifically on a couple of problems around grid shells that are familiar to many of you here. So I think experimentally you see that I might take a slightly different view on some of these problems, as well as on triaxial weaving, and these will be connected to the work of a wonderful artist, Alison Martin, that probably some of you know from this community as well. And our lab is based in the Institute of Mechanical Engineering at EPFL. And just a small correction on what Olivier said. So this is the SES, being the Society of Engineering Science. It's a small community of mechanicians that is internationally based. Okay, so we are based at EPFL at the Flexible Structures Laboratory. This is a little representation of my team, and we work on structural mechanics, on the fundamentals of structural mechanics. And of course, a lot of the work that happens in engineering around the area of structural mechanics, it's towards designing structures that are light, cheap, and strong. And typically, there's critical loading conditions after which things go wrong. What we try to focus on is precisely after the point of criticality on what is often called the post-buckling regime, and trying to look at an alternative view of regarding buckling as actually something useful with potentials for novel function. And so in this yin-yang of our work, we work on one hand on fundamental aspects of mechanics of these systems, always with an eye for applications, but certainly not going all the way to the type of applications that we're hearing in the first talk of concrete buildings and so on. Okay, so if I had to state the mission for what we do in the lab, so we focus on the yin-yang of buckliphobia and bucklephilia. So buckliphobia being the more traditional engineering perspective of trying to avoid buckling and regarding buckling as failure. By contrast, our focus on bucklephilia is trying to embrace buckling for novel modes of functionality. And since we focus primarily on slender structures that undergo these instabilities, geometry is a primary ingredient in this kind of of problems, and that also makes a lot of the phenomena that we look at scalable. And we might observe processes involving the mechanics of slender structures at the small scale. And so here is a picture of tearing of graphene that we've worked on with some colleagues in Paris, Benoit Romain and collaborators, and the coiling of carbon nanotubes on substrates, all the way up to the coiling of cables across the seabed. And so if I had to summarize or classify slender structures into 3 buckets, I would put them under the rods, plates, and shells. And we have active projects on all of these fronts. And so maybe the secret sauce of a lot what we do, which we jokingly call PDE, standing for Precision Desktop Experiments, is an experimental methodology to scale up from the small scale up to the centimeter, or down from the kilometer to the centimeter, towards really coming up with a insight into these type of problems. And we also do a fair amount of computation and theory, but we're primarily an experimental lab. So before I really get into the topic of the talk, just giving you examples of some other types of questions that we're currently working on. So we're very interested on the mechanics of knots, so how do knots work, with an eye towards developing a better understanding of surgical sutures. We work on these classic questions of shell buckling. So what are the knockdown factors of a spherical shell? Still a largely open problem, given the imperfection sensitivity of these kind of structures, and we're doing lots of experiments on this front. And we also like very much problems that involve interaction between fluids and solids, such as what happens in the flight of some funny-looking insects. So, but today the kind of functions that I want to focus on in utilizing buckling is using buckling for shaping, as for example what you might find in a tent, where you compress the end nodes to a distance that is smaller than the arc length of the beam, and as a result you buckled into 3-dimensional space. And if you connect it on how you dispose these structural elements in your initial layout, you can get shapes that are interesting. And so just an example of our view on bucklephilia. Now, these kind of principles are used or have been used recently also at the small scale. So this is a small video that hopefully doesn't get too messed up with the frame rate through YouTube, where buckling for shaping was used in stretchable electronics. So this is work coming out from the groups of Yong'an Guang and John Rogers at Northwestern. And here, the scale bars are just a few microns. And so by utilizing these mechanical instabilities, they were able to come up with these incredible micron scale stretchable electronic structures that have a variety of functions. For example, here's a solenoid that is used as an antenna. And so again, the theme of buckling for shaping. Okay, so today I want to tell you about a couple of projects, one involving the geometry and mechanics of elastic grid shells. There's a couple of papers from the past couple of years that detail what I'll be telling you in passing, and as well as the triaxial weaving, not in the standard way of weaving with straight ribbons, but using initially curved ribbons to essentially generate possible shapes that were not available traditionally. And here this is work that was inspired by some interactions with Alison Martin, who's a weaver and taught us everything that we know about weaving. Okay, so let's get going with grid shells. I'm sure in this community everyone is familiar with these reticulated structures, the most famous one probably being the Mannheim multi-hull in Germany by Frey Otto from 1975. And I mean the basis, and so here I'm borrowing a sketch from a think shell from Olivier and company that illustrates the basis of what is a grid shell. So you start with a layout of rods that cross at specific nodes. You then compress the outer boundary of this initially planar layout. So all of these beams or rods essentially buckle out of plane. And then you add an additional array of elements that essentially triangulates the structure and locks the structure in place. And so Olivier has done a lot of work on these type of problems, including here a wonderful example from the Soliday Festival in 2011 with such a large-scale structure. So these kind of principles of using buckling for shaping don't just work at the small scale like I was showing earlier in the stretchable electronic examples, but they also work at these very large scales. And these are two seminal papers, pioneering papers from Olivier and his collaborators that lay out a lot of the basis of what we know about grid shells. And what we're going to do for the rest of the talk, I guess I'll start from a slightly different point of departure with these PDEs, these precision desktop scale experiments, towards trying to gain some further insight into these geometric mechanisms and to illustrate these geometric mechanisms in a tangible way in a desktop experiment. Okay. So this is our experimental system. We start with a quadrilateral array of rods that are connected at joints. The rods are made out of nitinol, hyperelastic material that can undergo large curvatures without plasticity. We then have joints that are made out of this polymeric material that freeze the position of the crossings, but have essentially negligible torsional stiffness. And then the boundaries are pin connections that we 3D print so that the structure can freely choose the shape that it wants. Okay, and so now the problem is going to be one where we start with an originally planar layout with an outer boundary of the footprint in 2D. And then each of these outer nodes is going to move towards an actuated boundary that, of course, has smaller perimeter than the outer boundary to generate shaping. And so this is an example of the kind of grid shell that you might get when you go from a circular outer boundary to a circular actuated boundary. And so you have a bit of a mess. So you have all sorts of higher order buckling modes that occur. And so what we want to address is not so much the process of forward design, of starting with a 2D layout and seeing what happens, hoping for the best, but trying to say something about the inverse design. So if you want a certain target shape, what is necessary in terms of the original 2D layout to get there. And we'll focus on very simple shapes because we're really trying to get some fundamental understanding on some of these systems. Okay, so this is how we built our PDE on grid shells. So we these are hands of my former PhD student, Changia Bayek, the lead author of this work. And so we first lay out the nitinol rods. We then use these silicon-based polymer to essentially fabricate the joints through a casting procedure. Then very, very patiently, we attach these pin connections to the outer edges. And then we have some footprint templates onto which we attach these pins to realize different shapes. And so this is actually, I'm already giving you the final result here of one of our target structures, which was a perfect hemisphere. And you see that there's a lot of distribution of shear angles across the sphere. The spacing of the nodes at the boundaries is also non-homogeneous, and so we want to try to get some insight on that. Now, in addition to the experiments, we also do numerical experiments. Here we use a technique called the discrete elastic rod method, introduced by Bergu, Greenspan, et al. More than 10 years ago. And so this is a discrete language for elastic rods, where the discretization starts at the level of the energy functional and then employs some tools from discrete differential geometry to essentially arrive to the equilibrium shapes of, to be able to compute the equilibrium shapes for rods in complex geometric nonlinear configurations. And here I'm showing this little animation, a superposition of computed shapes. These are the black and on a white background lines, and then superpose those same parameters with an experiment, and you see that at least qualitatively the agreement is actually quite good. Okay, so this is one of our hemispherical grid shells, and you might think, well, how do I get to it? Well, you start from a circular boundary, and that will produce a nice hemisphere. Well, it's far from the case, and in fact, the solution given by Chebyshev many decades, a couple of centuries ago, was that you have to actually start from this rounded square and activate it towards a circle in order to get a hemisphere. So let me give you, well, so first, before I show you how to get there, experimentally, we then extract XYZ coordinates using laser laser profilometry to get the position of the nodes. So these are the red dots that are the experiments, the nodes of the experiments, and the black lines are the computation using the DER framework. And you see that the agreement, at least visually, is quantitatively excellent. Okay, so we have a couple of % deviation between the computed shapes and the experimental measurement. So now the theory of Chebyshev's, this was work done in collaboration with Andy Seichmann-Furners, who's an applied mathematician currently in Berlin. And he pointed us to previous work that he'd also done to Mark Pauly on Chebyshev net. So Chebyshev introduced the simplest description of a fabric, which is that of a quadrilateral grid, where the only thing that can happen is shearing at the node. So there's a warp direction and a weft direction. And so a Chebyshev net is essentially a map from a 2D domain to a Euclidean, three-dimensional Euclidean space that preserves all distances in the two directions of these filaments, of these rods, okay? And so the only thing that can happen is that there's shear at these crossing nodes, and the corresponding governing equation for a Chebyshev net is essentially relating the curvature of the structure to the shear angle omega, and U and V are the coordinates along each of the rods. Okay, so this is a hyperbolic PDE, where interestingly the characteristics are actually along the directions of the rod. Okay, and we'll see that this has some impact in non-local effects, as we know for these hyperbolic systems that are realized concretely physically in grid shells. Okay, so the solution for the Gauss equation for a Chebyshev net was arrived at by Chebyshev in 1878, and it was later revisited by Guis, a mathematician from Lyon, I believe. And we can plot it, and we can check if it works in comparison with our experiments. Okay, so this is the solution with the rounded square for the outer boundary, the circular actuated boundary. Black, which we had previously validated against the experiments, is the DER computation, and blue is the solution from the Chebyshev net that does not take any elasticity, any mechanics into the picture. And you see that the geometry goes a long way in giving you the correct actuated solution. Now, this is actually something that was a great surprise to us. You know, I'd been curious about pastel strainers for quite some time. They are a Chebyshev net. They are hemispherical. And my question was, well, maybe the Chebyshev solution might actually be hidden in a pastel strainer. And so we bought many pastel strainers. We cut them along the boundary. You then flatten them out. You bring all shear angles back to 90 degrees, and long and behold, look beautiful. So there's no fitting parameters, and the Chebyshev prediction for the rounded square was actually lying all along on these pastel strainers. And so again, this is not just a curiosity from differential geometry. It can really be realized in a system as simple as an item that you have in your kitchen. And so geometry really drives the 3D shape of these physical grid shells. And in this case, the pins are held by friction, so there's quite a bit more physics going on. And it's beautiful that geometry takes such center stage. Now, there are, of course, other solutions for Chebyshevs existing out there for cylindrical shells, for hyperbolic shells, which we have tested and compared with our computations. Again, black DER, blue Chebyshev, and you see that once again, geometry gets you most of the way. And so this is interesting because now we can start concatenating some of these unit cells to build up more complicated structures. We can, for example, concatenate a quarter-sphere in the cylinder to end up with a cylindrical-like dome. We can concatenate a quarter-sphere and the saddle to end up with a peanut-like pavilion, which we've also realized in experiments. Again, top is the actual experimental realization, bottom is the DER computation on top of experiments, and it's beautiful how predictive we can actually get to these designs. Now, beyond geometry, we've also tried to analyze the mechanics of these systems. And so, for example, the mechanical response is measured by a point load orientation somewhere on the shell. And the question that we were asking here was whether, well, this is a shell that is made out of rods, so is the stiffness, the rigidity of the structure primarily given by a shell-like quantity or by a rod-like quantity. So following the work from Reisner for indentation of a continuous hemispherical shell, the stiffness would scale like the thickness over the radius of the shell, whereas for a beam, we know that the stiffness will scale like the thickness cubed over the radius cubed of the shell. Okay, so what is the stiffness for a hemispherical grid shell? Is it more like a continuum shell, or is it more like an Euler-Bernoulli beam? And the answer is kind of partially trivial and partially fascinating. So these are some force versus indentation tests on these grid shells. Solid lines are experiments, dotted lines are DR computations, and so you see we must be either doing both wrong or doing both right. I think we're doing both right. So we have a linear regime here over which we can define the stiffness, and when we plot a normalized stiffness, here we're normalizing it by the Young's modulus and the diameter of the rods as a function of this dimensionless quantity that depends on the number of the structural elements we have in the system divided by this ratio cubed, we see that all the data falls along these straight lines. And so indeed, maybe this is the trivial result that the stiffness is indeed scaling like an Euler-Bernoulli beam. Now, interestingly, when we start doing experiments with different numbers of rods, so n equals 1 would be the trivial elastical solution, n equals 3 would be similar, closer to that very simple tent that I showed earlier, and everything follows along the scaling for a beam. But beyond n equals 4, so when you have more extended green shells with many elements, then all of the data collapses onto this line. So in a way, if I hide this n, it's trivial because the scaling goes like an Euler-Bernoulli beam, but the fact that the stiffness depends on n, it means that we have non-local effects at play, that even though the indentation is done locally, the local point of indentation actually measures, essentially gets affected by all of the rods in the system, okay? And so this is a signature. I don't have time to go too much into detail here, but this is a signature of this non-local behavior that is expected for this hyperbolic PDE, where information travels along the characteristics, and the characteristics are the rods themselves. And so it's actually a wonderful physical realization of a PDE. And we've actually studied this non-local behavior in a fair amount of detail, and I'll be happy to talk to you over the discussion later. Okay, but before we get to technical, I want to move on to the second topic of triaxial weaving with initially curved reeds, and this is to be contrasted with something that I'll call traditional weaving, which is what you'd see in straw hats and baskets, where the ribbons are naturally straight. Okay, and this is work done with again with Chang Yeb, Sam Pong-Klut, Tim Cheng, and our artist collaborator Alison Martin. Okay, so this is what really got us started. We saw some of the absolutely phenomenal examples that Alison has in her Twitter and Instagram page on triaxial weaving. So this is essentially a Kagami lattice of initially straight ribbons, and you see that by what she's really doing here is having different local arrangements for how to interlace these ribbons to arrive to these striking shapes. And here I'll do some advertising on the name of Alison. You might be interested in reading a wonderful profile that the New York Times wrote about her and her work, and some of the a workshop that she did in Sao Paulo. So this is probably one of the single connections I have with the previous talk. And I encourage you to read this article. It's very inspiring, and it was wonderful to see Alison featured that way. And that was a couple of years ago, I believe. I should have put the specific reference here, but if you search for Alison Martin, New York Times, you'll get to this article. Okay, so then we invited Alison to come and visit us at EPFL. That's not her suitcase with clothes. That's a suitcase filled with samples. And she came to EPFL, and for about 3 days, we essentially had a small workshop where she taught us everything that we know about weaving. And this is me sitting here with Alison and Chang Yeb, who led this work. Okay, so let's focus on a single example of a weave structure that she has fabricated. So this is Torres. So Torres, genus zero structure. So we don't actually need what is interesting here is that by following this traditional triaxial weaving approach, so traditional meaning with straight ribbons, you end up with curvature localized at some specific points, for a reason that I'll say in the next slide. And what I want to tell you in the next 10 minutes or so is what we have done to essentially bypass these regions of localization, and we end up with much smoother width structures that look like this. Okay, so here you don't really see any localization of curvature around the structure. Okay, so focusing first on traditional weaving, as some of you probably know, so three-dimensional shape is generated here by injecting singularities. And so in a triaxial weaving of hexagons, when you inject a singularity of a non-6 gon, and so something other than an hexagon, you generate three-dimensional shape. If the n-gon is has less than 6 sides, you inject positive curvature. If it has more than 6 sides, you inject negative curvature. And this is a very nice illustration from this paper that shows these mechanism. Okay, so we follow our usual precision desktop experiment approach, the PDE. We fabricated unit cells that are, we want to really study unit cell in detail. And so we use some ribbons that have a composite of metallic particles for reasons that I'll explain in a second. And so this is the unit cell that we want to study. And at the center of the unit cell, there's an n-gon that is defined by the edges or essentially by the center line of the ribbons, okay? And so now a question might ask, well, what's the curvature of the n-gon? And here, when I'm in curvature, there's no curvature in the void because there's no material there, so I have to talk about an integrated quantity, the integrated Gaussian curvature, where n stands for the number of sides that I have on the n-gon. Okay, so again, maybe I don't need to talk too much in detail about how we fabricate these systems. The unit cells are centimetric. And then importantly, what we do experimentally, we put them in an X-ray microcomputer tomograph to get the full geometric information that you might ever need. Okay, and so because we have these metallic particles on one half of the cross-section of the beam, we can actually filter them out so that we can separate the upper and the lower filament. And from that, we can then do some heavy image processing analyses to extract both the center lines. And by the way, I want to emphasize this is experimental data. The center lines that are the dotted, the series of dots here. And in addition, we can also compute the material frame. For those of you who are familiar with this kind of systems, the D1, D2, D3 triad that essentially tells us the orientation of the ribbons in space. So we basically have all the information that one might need to describe this system. In parallel, we also do some FEM. So here, the FEM done by Tim Cheng, a postdoc in our group. And we can then compare the data and try to understand. Okay, so when I told earlier about the integrated Gauss curvature, the Gauss-Bonnet theorem gives me a relation on how the curvature depends on the geodesic curvature of the center line of the ribbons, as well as these internal angles of the n-gon. Okay, and so in this case of traditional weaving with straight ribbons, we basically went and tested each of these various quantities in detail. So for example, here I'm plotting the sum of these angles of the n-gon as a function of the number of ribbons, and you see that everything stays constant, so around 120 degrees. If we now compute this geodesic curvature along the center lines of the ribbons, the geodesic curvature is 0. And this is a signature of the mechanics of ribbons. So ribbons don't like to deform in plane. They want to deform out of plane, and that's intrinsic to what ribbons do. And so this is basically a statement that the ribbon is functioning like a ribbon. And so the straight ribbon will have 0 Gaussian curvature from the start, and it doesn't get injected when we start buckling it and constraining it. So now, if I plot this whole quantity on the right-hand side, which gives me the Gaussian curvature, you see that I can only explore using this traditional system quantized levels of Gaussian curvature, since the curvature depends on this integer n, which is the size of the n-gon. Okay, so what we have done is by trying to bypass this traditional constraint, we have injected curvature in plane on the original ribbons and built unit cells that way. Okay, so for pentagons, hexagons, and heptagons, the traditional case is the one in the center where we weave with straight ribbons, but you see when we start weaving with other shaped boomerangs, for example, we could have a hexagon exhibit positive Gauss curvature or negative Gauss curvature. And we can essentially span those smoothly as I'll show in the next couple of slides. Okay, so now we're going to change the unit cell a little bit. So each of our ribbons is going to have 3 segments that are piecewise circular. And we can inject geodesic curvature by changing continuously each of the values of curvature, kappa 1, kappa 2, and kappa 3. Okay. And so the wonderful result, probably the central result of this part of the talk, is that by varying these kappa 1, kappa 2, and kappa 3, the piecewise curvatures of each of the 3 segments, we can now span the integrated Gauss curvature continuously. So we can essentially target and achieve any shape that we might want. We're no longer limited by this quantized level of n, because the Gauss curvature now depends on n, as well as this quantity kappa star, which is a linear combination of all of the curvatures of the unit cell. And I won't have time to describe how we derive this analytic. This is an analytical solution for this system. Okay. And so that is to be contrasted with continuous weaving. And so we can achieve a continuous range of curvatures. Okay, so I only have a couple of minutes left, so let me quickly go to the punchline. And so if we weave with straight ribbons, that is with geodesic Gaussian curvature that is 0 throughout the unit cell, we end up with a slightly rather faceted closed shape. Whereas if we are smart about where to inject this geodesic curvature, we can now, using curved ribbons, we can now weave very smooth shapes. Okay, so you can extend this framework to go beyond spheres, and here is a very simple inverse design procedure. Well, I can tell you more details during discussion of how we do this. We essentially have a target shape. We define the topology on the surface. We have a graph that connects the various ribbons. We have a way to define the local geodesic curvature, which we then try to match to the target surface. And using this inverse design geometric procedure, we can now start weaving non-spherical shapes. And so here is the example of an ellipsoid. We can do prolate and oblate ellipsoids. The ribbons now become, after this optimization procedure, become a bit more complicated. So we only need 2 different ribbons for each of these 3 structures. And here are the results for the first, for the second, and for the third structure. And the inverse design framework also works for tori, and the number of ribbons is now a bit more complicated, but the procedure is the same that I showed earlier. And so we can compute these simple canonical shapes. And you see now we get to back to the comparison between the traditional design procedure on the right-hand side and our new procedure using initially curved ribbons, and you see that the surface is indeed much smoother. Now you can go and quantify how different they are from the target shapes. We have done that. And, there's some, so the quantification here is on radial distance as a percentage of the width of the ribbon. And we essentially, in some places, we are a few millimeters off for an object that is 10 centimeters or so. Okay, so what is surprising here is that we haven't taken any elasticity into account to arrive to these structures, and so geometry is in the podium dictating everything that needs to be done. And of course, elasticity is then what's responsible for these hotspots of deviation from the target shapes. So here, I'll take this opportunity to also mention related work that Mark Pauly and his group have done. They've essentially taken these bases of weaving with curved systems, and they've done a full optimization that also includes the elasticity of the ribbons, and they've been able to show realizations of these free. Now they can do freeform. They're not restricted to the canonic shapes that I was showing you earlier, and they can produce these absolutely gorgeous structures with curved weaving. Okay, so last slide before last, where we heading next is to go beyond just geometry and trying to say something about the mechanics of these systems. We are loading domes that are triaxially weaved, and we are interested on the full loading path with snap buckling and quantifying all the various stable and unstable states. and this is turning out to be really very rich ground. And in particular, by changing the geodesic curvature of the ribbons, we can also control the sequence of buckling and amplitude by tuning this curvature. So from a more fundamental, we're not going to be building buildings out of these anytime soon, but from a fundamental point of view, I think there's lots of fascinating mathematical and mechanics research questions that we're addressing. Okay, so time is almost up, so let me just wrap up by summarizing what I did. So I hope I convinced you that bucklephilia, at least through these few examples I showed you, is an exciting area for asking research questions. So buckling is not just bad, but it can be used for function, even if the function is as simple as generating shape. So I showed you some aspects on the mechanics of grid shells, which I know are of interest to many of you in this community. I hope you'll enjoy this trick of using initially curved ribbons to generate smooth triaxial weaves. Here, precision model experiments at the centimetric scale, which doesn't mean they're sloppy. They're still high precision, even though the centimeter scale have been extremely valuable for us. And again, I think there's a lot to be done with grid shells and weaves, and where we're heading is, instead of going large scale to the architectural scale, we're actually trying to take some of these principles that this community is very familiar with to go small scale and design micro and micro scale structure. And I think that's exciting. So I'll just wrap up by thanking a few people. So Changia Bayek, my former PhD student who's now at Harvard, who led both of these projects. Andy, an applied math colleague who taught us everything we know about differential geometry systems. Khalid Jawed did a lot of DER computations in the first project. Sam and team worked extensively on the triaxial weaving together with Changieb. Alison taught us everything that we know about weaving, and we also benefit from many interactions we've had with Mark Polly's group, who also work on related themes. So now I wrap up, and I'm happy to take any questions. Thank you.
Thank you very much, Pedro.
Sure.
I think, I don't know, Cyril, do we have any question from YouTube Live? Or Romain, did you see any?
Not yet.
So maybe we can do the same and try to initiate the discussion. Maybe Romain.
Shall I stop sharing, Olivier, or shall I leave the slides on?
Maybe you can stop sharing. I don't know. Yeah.
Okay, that's me now.
Okay.
So maybe Romain can initiate the questions.
Yeah, so thank you very much for your presentation. I found it really interesting and fascinating.
Thank you.
It's also, I think, in our... sorry, Chris, I will just mute you.
You have to stop your speaker, Chris, if you want to.
Yeah, I did. Or yeah, because there is a feedback.
Or YouTube. There might be a feedback from YouTube if YouTube is on. I don't know.
Oh,
okay.
Yeah.
Can you hear me now?
Yeah.
Yes.
Yes.
Right. Good.
Please, Chris.
Thank you very much, Pedro. That was very interesting.
You're very welcome.
I was lucky enough to have worked on the Mannheim grid shell.
Oh wow! Nice. Wow.
With Ted Happold and Ian Little at O'Varop and Partners, with Friato, of course. And well, it's not really a question that I've got. It's more a comment, and that is that the big problem with Mannheim was creep buckling, or is creep buckling, I should say, in the sense that it was originally designed for 20 years, but it's now over 40 years old, and it's slowly creeping. We were very aware of that during our work on the project. But the way that we looked at it in the end was to say that collapse is a short-term phenomenon. It happens quickly. And creep prior to collapse is more like an increase in initial imperfections. But of course, what happens is that as the initial imperfections increase, the moments go up, and therefore the rate of creep goes up, and you end up with this difficult situation. I suppose the other point was that Mannheim was a double-layer grid shell. In other words, there are two members going in each direction. And of course, the reason for that is that you need the flexibility to be able to bend it into shape. And then you try and lock it into shape by connecting the upper and lower members to act compositely. So perhaps I do have a question, and that is, have you done any work on double-layer grid shells? But thank you very much for your talk, and it was very interesting. And it was nice to hear you talk about Alison, because we know Alison in Chalmers in Sweden. Because
of course, yeah, I know that she's had an interaction.
So thank you very much. And so now I should turn my microphone off, I guess, and then I can turn my speakers back on so that I can.
If you stay with us,
okay, right.
If you stay with us during the question, you can leave it like this. If you leave the stage, you have to put your YouTube live on again. But stay with us.
Oh, sorry. So I'm not sure if I can hear, and I know what I should do.
Oh, but we can turn off your microphone, and you can put your speakers on if you want.
Okay, so Chris, I don't know if you can hear me now, but yeah, thank you so much for your comment. It was wonderful to hear that you that you were involved in such an iconic structure. And so maybe to answer your question first, I haven't done any work on double layer grid shells, and I understand that the double layer rationale for the Mannheim was also part of the fabrication and also the locking of the joints to hold it in position. Maybe here Olivier has a more experience in this area in terms of the larger scale structures, and so there's not much that I can say. I think it's interesting, but it's probably the constraint of going for that solution was really more to do with fabrication, as I was saying. As to your comment about creep buckling, so I probably wouldn't interpret it as creep being analogous to an increase in initial imperfections that essentially can lead to buckling, because as I was indicating earlier, the mechanics is really driven by beam-like mechanics rather than continuum shell-like mechanics, and so I would tend to point that the buckling of these systems is imperfection insensitive, unlike continuum shells. And maybe here again, Olivier, maybe you can back me up if your earlier work on buckling of grid shells indicates that or not. I think it's just perhaps more to do with the fact that you're exploring the configuration space of the system, and then at some point you actually get closer to another energy minimum that is preferential, right? So it snap buckles or it buckles into a new configuration. And interestingly, we're addressing precisely this question, but on the triaxially weaved domes instead of green shells. And here we see that the solution space has all these stable states flying around, and so again, the transition between one and the other is very important. We're trying to understand exactly what are the underlying mechanisms. So maybe Olivier here, can you help me out on both the double layer grid shells and whether you found any evidence for imperfection sensitivity in grid shells? I haven't, and I think they behave like beams in their stability.
Yeah. Well, for me, beyond all of this, I think what you have shown in your presentation is a unbrace grid shell,
Mm-hmm.
and I think it's quite well. We know that if we brace it, we get a shell behavior, and the stiffness is increased by a factor of 15 or 20, and for me, I would rather ask you the question why you didn't try to brace the structure, and you stayed on a grid shell unbrace, so it's not really a grid shell.
Remember, yeah, exactly. Okay, so we didn't brace it on purpose for two reasons. One, we want to really get down to these geometric principles that underlie grid shells, and the vision to doing so is that we still want to devise mechanisms out of them, right? So we actually want them not to be stiffer by 15 by a factor of 50.
Yeah.
We wanted to actually go micron scale and for example, generate valves and pumps, and for that you actually want to explore the solution space. So these are not load bearing structures, and here this is probably what distinguishes maybe some of the work that we do from the focus of the architectural geometry community. We actually want to embrace the large deformations that might entice, and so also because the bracing case had also already received a lot of attention. So we wanted to come up with devices out of it, and it's been a long process, and we're not quite there yet, but that's where we're heading.
Okay, I fully understand, and it's true that the kinematic of buckling of unbraced shell is really interesting. Of course, not interesting in our part of advanced architectural geometry. At the scale we're working, not so much, but at a smaller scale, it's obviously a huge potential.
Of course, and here I think something that is very valuable, and I thank you again for inviting me to come and be present at this conference, is precisely this cross-pollination, right? So there's lots of things that this community knows and has known for a very long time that when ported maybe to the microfabrication community, and I gave this example of stretchable electronic components that essentially use the same mechanisms for shaping, and I think it becomes very rich, this area of interactions, right? So again, I thank you again, and I think there's things that I'll learn from this week that I can hopefully port back to other length scales, to other areas.
Yeah. Well, we are also very happy to have you and to mix the experience and the field is always something that enriches the community. And maybe Romain wanted to ask a question.
Yes. So I had a question, but I see also a question in the live feed. I think quite related to what I wanted to ask. So first, maybe I will ask my question, and then I will also ask the question by Sergio Pellegrino.
Oh, Sergio.
Yeah. So I was wondering if you had the same kind of scaling effect with respect to essentially the individual bending stiffness of beams on the the number of buckling modes that you get when you're just in the first part of your talk, when you just mentioned that you move the supports. I guess you should expect to have this kind of behavior, or like the same kind of non-dimensional number. And then I come to, so that's my question. And then the question by Sergio Pellegrino is, hi Pedro, I'm thinking about a link between the first and second part of your talk. Do you find that the stiffness of the grid is proportional to T over R if the width forms triangles? Which is also a very, I think, in the sense of the discussion we just had.
Yeah, so, Roman, thanks for your question. It was great to hear from Sergio, who I know very well. Okay, so I'll be careful in the answer to the second question because we haven't studied in detail. So I don't want to say anything that is wrong, but that I think an important thing to do now with triaxial weaves is essentially to try to characterize the mechanics, starting by the stiffness. So doing similar work that we did for the grid shells and going all the way up for triaxial weaves. Now we have all these possible states around, and we're trying to first characterize what are the basins of stability before we dive deep into it. So the answer is we don't have that yet. We're working on it, and to me it's not clear, right? Because the topology of this Kagome lattice will be different than the much simpler grid shell system that is not braced, where shearing can do what it can. It's just the position is constrained. And so I want to be careful. These systems end up exhibiting a lot of non-trivial behavior, so one has to be careful. And that's where these experimental model systems are very useful, because you can actually go and test them out, right? And so, Sergio, we'll talk about that your question hopefully a few weeks from now when you visit Lausanne, or a few months from now when you visit Lausanne. So for the first question was around. So remind me, Romain, I kind of got lost.
So it was regarding the number of buckling modes you observe when you're just moving the supports. I guess it depends on the kind of a T over R ratio, but not this one. More like
but you see the internal so the internal constraints of the grid. excite higher buckling modes in a way that is not so trivial to rationalize, huh? And so indeed we can excite higher buckling modes than just the first one that we were trying to get by using Chebyshev solution. But saying exactly how many get excited depends so much on the way that the grid is inducing the constraint that we don't have that insight, nor we have theoretical tools that we have developed to address that. We have studied multi-stability, or at least to try to identify when we have monostable or multi-stable states, for the case where you go from a circular outer boundary to a circular actuated boundary. And there the primary, I actually had a slide on that. I mean, I could try to pull it out if you're interested. But the most important part is basically whether the outer boundary induces a topological defect. So you have a square grid. If the boundary essentially cuts one of the nodes out, you increase the number of modes, and essentially then down to the length of these outer legs that are near the boundary. And so we have quantified when you have monostable and when you have multi-stable, and that again is just to the length of these legs. But then when you have multi-stable, to say how many states we have, I'm afraid I don't have much anything intelligent to share. Chris, maybe I had a question for Chris. I mean, I'm fascinated maybe to learn a bit more about the process of how the whole team came up with Mannheim. Were model systems realized to try to get some insight of what would be the outer shape? I mean, at the time, of course, computational tools are not what they are now. So I was wondering if you could share a little bit about the methodology that you followed in the design. Okay, I think you're muted. Still muted.
Chris, you're still muted.
It should be working. Yeah.
Okay.
Chris, in the Jitsi, you have to down and mute yourself.
Should be working now.
Okay. Sorry. Okay, so maybe, if there's any other questions.
Maybe Cyril has some questions. Cyril worked and did his PhD on grid shells. So
sure,
maybe, Cyril, do you have questions?
No, the question may be a remark, because we just released a study on the grid shell I had studied during my PhD, and that was demanded about 6 years after. And that constituted a kind of relaxation experiment. Of course, it was not made of wood, and it was at architectural scale. And what we observed was no really damage due to time of the material, because we kept as the limit, the strain limit, relatively low, about 30% of the strengths, and so that the creep could be seen rather as a positive issue, because of the bracing, it was actually not creep but relaxation, and permanent stresses were diminishing during time. So that because in the case of GFRP, there is no damage, or the moduli doesn't change during time. In our case, the time and creep was more an advantage than an inconvenient.
Right, because of stress relaxation. Okay, that's interesting, right? And
so, can you hear me now?
Yes.
Okay.
Perfectly.
So I discovered that if you go onto the stage and then after Cyril mutes you, then you can't unmute yourself. So what you have to do, you have to go off the stage and then go back on again. So that seems to work. So Yes, well, Fayato built a hanging model, a hanging chain model, because the idea was that, as you know, a grid shell is very much a mechanism, so that under own weight, when you invert it, you end up with a funicular shape with theoretically no moments. That was a very accurate model, but the structure was actually built from a computer model by link bits. We did buckling models in our office, and we also did computer analysis on the CDC 6600 on a very coarse grid. What we found was that because the structure is designed as a funicular shape, even though, I agree with you, that grid shells are basically not particularly imperfection sensitive, but what happens is that as it moves away from the funicular shape, then the dead load moments increase. So if you have the true funicular shape, then you have no moment. If it deforms a bit, you start getting moments. And it's those moments which then increase bit by bit with time, meaning that, if you like, the imperfections are increasing, and therefore the rate of creep increases with time. But probably collapse, if it occurred, would, well, hopefully it would be after quite a large amount of creep deflection, but quite a large amount of creep deflection has already occurred. So there's now detailed discussions about what to do with it in the future. Although that's less of a problem, I think, than finding a function for it in the future. So it's not an architectural problem, in a sense, more than a structural problem.
Okay.
Great. Thank you very much.
Thank you.
Thank you. Just one question about the second part of your presentation. You never cited the word geodesic line, but apparently these elements are following, if they are straight, they are following geodesic lines. And it was not clear, because you could do a pattern with geodesic line, but maybe your constraints were to get a spacing that was even along the mesh.
Yeah, which is something that then that's because we wanted to follow a unit cell approach so that we could really control the small scale geometry, and that's a constraint that Mark Pauly in his recent work has relaxed. And so in the full optimization, inverse design full optimization procedure, they can also change the spacing, and that's then what allows you to get these more general arbitrary shapes. But yeah, so maybe answering it differently, still connected to the unit cells and the spheres and the ellipsoids that you saw, the curvature of the ribbons in plane, and so we cut them with a laser cutter, right? So a specific shape, we cut them with a laser cutter. The curvature of the ribbons in plane, when mounted because of this constrained spacing between the nodes, is essentially the geodesic curvature of the ribbons, right? And that's what allows us to then compute these three-dimensional shapes and realize them, right? And that's the trick. And this is a quantity that can be changed continuously. Hence the difference of the discreteness imposed by the injection of singularities if we have straight ribbons, right? Because you have no geodesic curvature because the ribbons are originally straight, and so you have to inject curvature by these singularities. Anyway, it's kind of, and of course we all use computational tools and sophisticated sophisticated numerics, but there's nothing, to me, I'm an experimentalist, of course I'm biased, but there's nothing like playing in the lab, right? So going to these models of hanging chains and so on, there's often things that you learn that were really unexpected. And these literally came, like we were sitting around the table with Alison and my student, she was teaching us how to weave, and I said, well, I'm wondering what would happen, and very naive question, what would happen if we actually used curved ribbons? So we ran to the room next door, we laser cut some ribbons out of mylar, I think, and we started weaving using the same technique that Hallie, and then we said, like, oh, if you have something curved and if you weave a hexagon, you'll actually generate curvature. And then it was only much later that we will rationalize the the underlying mechanism. So yeah, so playing around in the lab sometimes gives you surprises, and that was definitely and that was a really nice moment. That afternoon we were super excited, like, oh, new way to weave smooth structures. But anyway, so back we can change the geodesic curvature continuously, and I think that's the crux of what I was trying to tell.
Okay. I think we've gone through the time or well beyond, and I think we could speak forever. So maybe we should stop. Thanks again, Pedro, for this very nice online conference. Just for the audience to meet up, I propose that we all go to the pavilion area, and then we can have either a small discussion in between two persons or larger discussion in a pavilion. And at 8 o'clock, I propose the authors of tomorrow and the moderators of tomorrow to go to the room TESS on the map of Paris on the top left corner. We all meet there at 8 o'clock to really look at all the details for you to well understand how it works. Okay, so let's all try to move to now to the pavilion area. And thanks again, Pedro, for your talk.
Thanks for the opportunity. It was fun to try out this new format. I think it really works. Thank you.
Thank you very much.
Thank you.
See you in the pavilion area.